Hey there! Today we're going to talk about the theory of games. In the first part of the course, we'll do a little introduction, meaning we'll give a presentation on game theory. We will start off with a quick overview of the so-called simultaneous game in the first part, then we will move on to the sequential game in the second part. Finally, we will do a simple exercise together in the last part, just to provide you with another example. So I would say that we can obviously commence with our slides. So initially, let's provide a definition to the theory of games. Let's assume it is a situation where two or more parties are required to make decisions that also rely on the decisions made by other parties involved in the process. This definition is super important, just to give you a practical example, because they will be the two examples we will consider later on. One is the game of chess, and one is the game of rock, paper, scissors. What occurs or transpires in both of these games? The final result is not only dependent on your choice and decisions, but also on the decisions made by other individuals, emphasizing the impact of external factors. Why rock, paper, scissors, and chess specifically? Because at this moment we are going to witness gradually the distinction between a sequential game and a simultaneous game. In simultaneous play, the two players, or three or four, we'll use two players as examples, choose together like rock, paper, scissors. So, when you play rock, paper, scissors with a friend, 1, 2, 3, then there's always someone who cheats and waits. But actually, when you play the game, theoretically, you should throw together, choosing together. In sequential games, like chess, is like I choose, you choose, I choose, you choose, one after the other. Let's go check out some details about game theory in general, then let's move on to simultaneous play. So the elements are two or more players, although we will stick with two players, strategies, which are actions or sequences of actions, and payoffs, which are the final results or rewards or utilities that we obtain. Let's go check out the first game. So the first game is a simultaneous game. Like we were saying earlier, the players move together like rock, paper, scissors. In the oligopoly, the simultaneous game is Kurno. In the next class, which I still have to register for actually, but probably by the time you see this video, it will already be registered and probably already available, we will talk about the oligopoly. Oligopoly is closely linked to game theory, and in oligopoly, typically three models are used: Cournot, Stegelberg, and Bertrand. Bertrand is when they compete on prices, which we'll put aside for a moment now. We have Cournot and Stekelberg. Cournot and Stekelberg are two models where we have two companies, a power duo, and in both games they compete on quantities. They compete on quantities. The difference is that in Concourno, they compete on quantity by deciding together the quantity to produce, so simultaneously, while in Stekelberger one decides first and then the other, first one company and then the other, so they decide sequentially. Generally, when encountering a simultaneous game, it is typically represented in the form of a matrix, with player 1 and player 2 as the key entities. The strategic actions available to player 1 are denoted as AB, while player 2 also has the options of AB. Within the matrix, the payoffs that can be obtained by player 1 and player 2 are specified. For example, if player 1 chooses action A and player 2 also selects action A, the question arises as to where their paths intersect and the outcome is determined. So, what's happening in this little square here? 3 will be the payoff of player 1, meaning if they get here, 3 is player 1's payoff, 4 is player 2's payoff. Remember that therefore the first number, the one to the left of the decimal point, is the payoff for this player. While the second number, the one to the right of the decimal point, is this player's payoff. If player 1 chooses B and player 2 chooses A, they end up in this square. So player 1's payoff would be 4, player 2's payoff would be 3. Now you see, I divided them with colors to make you learn quickly and in a simple way. Obviously in the exercises not all the colors will be there, so remember the left side of the comma, right side of the comma rule. If player 2 chose B and player 1 chose A, they would end up in this square. So 2 would be player 1's payoff and 3 would be player 2's payoff. If player 2 chose B and player 1 chose B, they would end up in this square. 3 is the player 1's payoff, 2 is the player 2's payoff. How can we solve a game of this nature? Therefore, in order to solve this game, we must commence by choosing one of the two players involved in the game. Let's assume we select player 1. What is our course of action? Given that they make the decision together, player 2 must choose either option A or option B, assuming that player 1 will also choose either option A or option B. So, player 2 responds, alright, if player 1 opts for A, what course of action should I take? If player 1 chooses B, what's the best move for me? And that's what we're doing now. Let's assume that player 1 chooses A. If player 1 chooses A, it means that we'll be in this rectangle. So it means that we could end up either here or here. What's the best move for player 2? Pick A or pick B? If you choose A, you'll have a payoff of 4, because it will fall here and has a payoff of 4. If you choose B, you get a payoff of 3. So we're going to choose, since 4 is greater than 3, player 2 will choose A. And thus, we place emphasis on the number 4. Now let us assume that player 1 selects action B. Therefore, if player 1 were to choose B, what would be the consequence or outcome for player 2? What is the best move? So if you choose A, you have a payoff of 3. If you choose B, you have a payoff of 2. Since 3 is greater than 2, obviously player 2 will choose A, and therefore we underline the 3. At this stage, we need to take the opposite approach for the other player, assuming that player 2 selects option A. If player 2 chooses A, it indicates that we will be in this particular column, potentially ending up here or ending up in the range of 3 to 4. Clearly, 4 is a higher value compared to 3, because if we end up here, player 1's payoff is 3, whereas if we end up here, player 1's payoff is 4. Since 4 is greater than 3, player 1 will undoubtedly opt for option B, and we place emphasis on the value of 4. Let's assume player 2 picks B, and then we will be in this column as a consequence of their choice. What's happening? If player 1 chooses A, we're done here, and player 1 gets a payoff of 2. If player 1 chooses B, we'll end up here, and player 1 will have a payoff of 3, 3 greater than 2. So let's underline the 3, and in that case, player 1 would choose B. At this point, now that we have done both options for both players, we need to go see where we have highlighted both numbers. The solitary option where we highlighted both numbers is this particular one. Therefore, it indicates that our Nash equilibrium is precisely this specific option. That is the Nash equilibrium we have. The Nash equilibrium represents the best response to the strategy employed by the other player in the game. So, if we wanted to provide a definition of Nash equilibrium is the state of balance that is achieved when every player selects the optimal strategy in reaction to the strategies of the other players. As a shortcut for exercises, that is essentially the location where both numbers are underlined. It's a shortcut, okay? Don't say it like that, but it's a way to grasp how to do the exercise. There was a little quirk here. What was the special feature? The thing is, if you notice, player 2 always chose A. I mean, in case player 1 had chosen A, you would have been here, and player 2 had agreed to choose A as well. If player 1 had chosen B, you would have been here, and player 2 would have been better off choosing A another time. Let's assume that player 2 would have chosen option A, regardless of player 1's choice, just for the sake of this scenario. So what does it mean? It signifies that player 2 had what you might refer to as a strategy that was dominant in nature. Let's go and see what it means. A dominant strategy is a strategy that is chosen by the player, regardless of the strategy that is chosen by the other player. Player 2 would have chosen option A regardless of player 1's choice, but if we notice, even player 1 had a dominant strategy because he always chose B, 4, and 3, never 3 and 2. That is, never A, always B. So even player 1 had a dominant strategy here. When the Nash equilibrium comes from two dominant strategies, it is called dominant equilibrium. So dominant strategy, equilibrium, we have seen. So dominant equilibrium, equilibrium, that is obtained if both have dominant strategies. Here is the game in a complete way. So we have seen what dominant strategy means. We have seen what dominant equilibrium means. We have seen what Nash equilibrium means. But what does Pareto optimality mean? Pareto optimality is a situation in which there is no possibility of moving to improve one player's payoff without worsening the other player's payoff. What does that mean? Let's go back here. This was our Nash equilibrium. Is there a way to get around this place? Moving from here means moving instead of staying here, going either here or here or here. That is, in one of the other three quadrants. Is there a way to move improving the payoff of one but without worsening the payoff of the other? Let's see then, if we move to this high, well, player 2 would improve because he goes from 3 to 4, but player 1 would go from 4 to 3. So let's say he improves, but he worsens. If we move from here to here, player 1 worsens because he goes from 4 to 2. If we move from here to here, both worsen because from 4 to 3 and from 3 to 2. We cannot move from this location and enhance the payoff of one without deteriorating the payoff of the other. Then this is referred to as Pareto optimality. Allow me to provide you with the contrasting example. Observe what occurs if you are in this position, but if there existed the potential to relocate from this quadrant and proceed, for instance, to this position, what transpires is that you enhance the payoff of player 2 because you transition from 2 to 4. And for player 1, you remain at 3, so we can assert that you do not worsen the payoff of 1. Therefore, in this scenario, you possess the opportunity to move from this location, enhancing the payoff of 1 without worsening the payoff of the other. Hence, the shortcut is the query you must ask yourself is, am I able to move from this location, enhancing one without worsening the other? All right. If the answer is yes, that's not a great Paretian. If the answer is no, then that's a great Paretian move. I'm wrapping up this part of the course with a little something extra. Sometimes you might be able to solve the game with iterative elimination, meaning it can ask you the exercise. What is an iterated strategy? It is a way to find the Nash equilibrium by eliminating dominated strategies. Do you remember before we said that both players had dominant strategies? All right, now we're going to go and eliminate the dominant strategies. Let me give you an example. Let's look at player 2. If you look at player 2, when he chooses A, he can get either 4 or 3, depending on what player 1 does. What do you notice? That strategy A dominates strategy B, because if he chooses A, he gets either 4 or 3. If he chooses B, he gets either 3 or 2. So either way, it goes from 4 to 3. So if player 1 chooses A, it's still better to go with 4 than 3. If player 1 chooses B, anyway 3 is greater than 2. So at that point, strategy A is convenient, even if player 1 chooses B. So, as we saw earlier, strategy A always pays off. So strategy A dominates strategy B. If there were 5 here, let me give an example, then it wouldn't be valid anymore. Why? Because strategy A was convenient when 4 was greater than 3. That is when player 1 chose A. But if player 1 had chosen B, strategy A wouldn't have been convenient anymore, because 3 is less than 5. So we're going to get rid of this dominated strategy and we'll get this, meaning we've eliminated part B. Now let's move on to the other player. The other player, we see that at this point he only chooses A, so there's no big, let's say, big efforts to make. You can immediately see that if player 1 chooses B, they have 4. If player 1 chooses A, they have 3. 4 dominates 3, so strategy A is dominated. And so we've also eliminated this one, strategy A, and we've found our Nash equilibrium. All right, see you in the next part of the course to check out the sequential games.